Hello there and welcome to a new video. Yeah, sorry it's been a very long time since I last uploaded. Frankly, I've just been lazy, I have to be honest. And also, good luck to all the new bred year 12s and 13s with their A levels. Don't fail. The school needs passing rates and, you know, A stars and A's. So make sure you keep that up, yeah? Superb. Now, I already recorded this, but there was one fundamental point which I completely forgot about. Gravity. I didn't talk about it in the last video because I tried to do it in one take and it was just unsuccessful. So anyway, I've already written some of that out anyway. Okay, let's just talk about each and individual point that I've written so far. So, constant acceleration. These are what they stand for. So, these are the SUVAT equations. Now, displacement, I've already kind of explained in terms of this graph. So, the total distance in which, if you walk like this from point A to point B, if you walk all the way around just like a Swiss off-road, then that's the total distance you travel. Whereas literally just point A to point B, just a straight line, is how far of a point is A from B or the other way around. That's the displacement. Okay, so that's what it stands for. We use the symbol S. U is the initial velocity. When you're talking about projectile, it's called the speed of projection, usually at an angle or a 90-degree angle if it's going upwards. V, that's a V, is a final velocity. So final velocity is obviously the final velocity. I don't know why I said that. And the acceleration, A, and obviously T is time. So pretty just simple stuff. The SI units, so displacement is measured in meters because displacement and total distance are almost identical. Initial velocity and final velocity are both measured in meters per second. Acceleration is measured in meters per second squared. And time is in seconds. Just remember that you may have to convert your measurements from miles per hour into meters per second or minutes into seconds, for example. The reason for this is that you could end up with the completely wrong answer. End up with a final velocity greater than the speed of light, for example, or whatever. Just be very, very careful what you're looking at and make sure you convert your units properly into meters per second. Make sure it's SI unit. Don't put meters in terms of like inches, feet, like the Americans. There's just absolutely no point. We go by standard international units. Okay, so let's talk about the equations here then. Here, and these three are your equations. If you want to pause, then by all means pause and then just take these down. So what I'm going to explain is that these two, during my entire A level, these two cropped up the most by far. They cropped up in almost every question. This crops up quite a lot. This is definitely the least common. You could last the entire A level without using this equation. You might use it for like 1 or 2 questions throughout the entire year 12, 13 or whatever. And then this equation is for, yeah. So there's a common theme with these 5 equations. There's always one variable missing. So what I mean by that is that this one doesn't feature acceleration. This one doesn't feature displacement, time, final velocity, and initial velocity. Doesn't feature at all. That's because, going back to here, if a question doesn't include any include the one that it doesn't show, you know which equation to use. So, for example, if time isn't being used, if we have displacement, initial velocity, final velocity, and acceleration, we can use this equation because we have already 4 variables. We already know the 4. Even if we have, look, even if we have 3 variables, if we need to find the final velocity, we already know what equation to use. And if we need the acceleration, we can just rearrange simply. It's very clever, this, I have to admit. Okay, let you take down a pause or whatever, and then onto graphs. Oh, graphs are so much fun, aren't they? Okay, velocity time graph. What's happening here is that we have a positive gradient, a zero gradient, gradient 0. No, sorry, that there isn't. There's a flat gradient. I don't know. I can't remember the technical term for it, but there is one. I just can't remember the name of it. And then we have a negative gradient here. Okay, so with this velocity time graph, what it means to have a positive gradient on the velocity time graph is it's accelerating. There's a constant acceleration occurring when you increase speed. So we're going from speed U to V, and we are increasing our speed with respect to time. Just remember that time is always on the horizontal axis, always, no doubt, no question. So the flat gradient means that there is a constant velocity. So you're still increasing your displacement or distance, and then your negative gradient is what's called your deceleration or retardation, if you're that much of a child to use this word. Okay, so I'll go through it again. So the change in velocity over the change in time is equal to the acceleration. So when the velocity is constant, i.e. the flat gradient there, the acceleration is equal to 0. So this is just a constant velocity. Negative gradient is a deceleration or retardation. And the final point I would like to make is, I know I put an integral here. So obviously an integral means an area under a curve. So we're not, obviously you can use integration if you find a formula to use to find an equation, but there's absolutely no point. If there is no equation being used, then what we usually do is, I've already done this for you, we split this up into individual trapezia, square, rectangle, or triangles. And then we solve it from there. So the area underneath the velocity time graph is the distance traveled, or the total distance, I'm not entirely sure. Okay, that pretty much sums up velocity time graphs. Let's move on to displacement time graphs. So with displacement time graphs, there's no point working out anything underneath the curve because there is nothing to work out. A positive gradient indicates, a positive or negative gradient indicates a constant acceleration, constant velocity. So constant velocity moving upwards or moving downwards, straight line. Now, when you have a constant displacement, that means the velocity is equal to 0. Therefore, the object is stationary. The object does not move. You know, 0 velocity, you're not going anywhere at all, are you? Therefore, what, you know, is what it is. So, this curve here indicates an acceleration or deceleration. So in this case, there is a deceleration. Okay? What's happening here is that it is moved quickly at first to go to this back to the same point, but then it's slowing down and then going back to, and then it's just, so basically it's moved quickly and then it's slowed down back, almost back to the same point. Okay, so what's happening here, these are two different examples of what the acceleration could be. What I mean by could be is that there's two different, obviously, types of curves. So with this one, where my pen is pointing at, it is moving off slowly and then it's gaining velocity. Okay, so it's gaining constant velocity. Whereas with this one, it started off very fast and then it's moving off and then it's moving very slowly afterwards. Usually with this type of graph, on a constant, on a velocity graph, typically it can mean terminal velocity. But anyway, that's for another time. So, the acceleration time graph. This one's the most complex, I would say, out of them all. What's happening here is there are two sides of this graph. So where the time axis is, if you're above the time axis, you're accelerating. If you're below the time axis, then you're decelerating. Okay? So what's happening here? When there is a straight line above the x-axis or the time axis, there is a constant acceleration. When it is a straight line with a zero gradient, okay, there's a constant acceleration. Typically, yeah, never mind. I forgot what I was going to say. When it is on the time axis, for example here, there is a constant velocity. Because obviously there is zero acceleration and then it's still moving, but there is no increasing speed, decreasing speed and whatnot. And then obviously here, I obviously changed terminologies. When it's below the time axis, there is constant retardation. Okay? Now, just like a little fact or two, when there's a straight line here, this indicates a constant jerk. Yes, I know it doesn't sound, you know, appealing, but that's the terminology. That's what it's called. So the derivative, so whenever there's a gradient of acceleration, so the derivative of acceleration is jerk. And then obviously you have a negative jerk. That makes sense. So change velocity, change in acceleration over the change in time equals jerk. This is measured in meters per cubed. And underneath the graph, so underneath the area of, say, this square, is the velocity. Yeah, that's it. Obviously between two individual times. Okay. Finally, the bit that I would like to get onto. Now, let's talk about gravity. Now, gravity is a strange one because obviously you have Newton's force of gravitation. No, sorry, Newton's law of universal gravitation, which suggests that there is a force. There's a centripetal force No, sorry, not a centripetal force, but there could be. There is a force, gravitational force between the sun and the earth, for example. Other suggestions could be a centripetal force because it's an orbit. And obviously you have space-time, which obviously means the larger the mass, the more you're pulled in, the more heavier you become, let's say. Other meaning could be gravitons. We don't know about that, if we can consider it in the standard model, which it isn't. We don't know yet. Anyway, sorry, going off track. Gravity. When we talk about constant acceleration, it's important to note, let's say if we have a ground zero, for example. This is just the ground, for example. Nothing special about it. It's just one piece of very, very, very slightly curved ground. The Earth is not flat, kids. Don't forget that. Anyway, when considering anything about in this case, in this video, we're only going to discuss about if it's going upwards or downwards. That's it. That's what we're discussing. We're not going to talk about projectiles just yet. So, what's happening is that, obviously, when you have a ball in the air, and you're going to drop it straight to the ground. You have information, but you don't know what the acceleration is. Oh, of course you do. Of course you do. 9.8 meters per second. And it approximates in maths, in the maths A level, you approximate it to 9.8 meters per second, whereas in physics, it's literally just 9.81 meters per second. Look at the front of your question paper and make sure what they want, or 10 meters per second squared. Either way, it's just an approximation. It just depends what they want. It depends what they're asking as well. And, you know, if you can get marked down if you use the wrong G, which is annoying because I've used 9.81 in maths, and you could get the actual answer and the mark scheme slightly wrong. So you just have to be really, really careful on what you're doing and what G you're using. Typically in maths it's 9.8, in physics 9.81, but just be careful. Just be really careful. And obviously G G differs across the world. For example, in the Hudson Bay, it could be like 9.6 meters per second squared, whereas say somewhere like, I don't know, the Netherlands, it could be 9.82 meters per second squared. It just depends. It really depends. Okay, so when it's going down, the acceleration you must consider is 9.8 meters per second squared because it's going downwards. Whereas, also considering this, the positive direction as well. Also, I almost forgot again, make sure you know where you are positioned, well, what direction you're considering. Because if this is the positive direction, then if the ball is going upwards, then the acceleration is minus 9.8 meters per second because it's decelerating as it goes up because gravity goes down. Does that make sense? Should, definitely. So, that's what happens. That is what's happening. Unfortunately, there isn't really much more to explain. So what I'm going to do is I'm just going to go through 2 examples with you, and then hopefully you can solve the rest or whatever you want to do. Okay? Alright, sweet. Let's go into the questions. Okay, Doug. Right. Let's see what's happening. Let's draw a graph to visualize what's happening. So this is the ground. The ball is 7 meters above the ground. So what's happening here is that it reaches a point of greatest height, which we're going to call S. And then, obviously, it's going to travel back down to the ground. Okay. Okay. That's what's happening here. So that's the graph we can consider. Right. The typical, usual, proper, not method, but collect all your information. Okay. Also, we're going to consider this, the positive direction downwards, because it's really important. I prefer, you can put it upwards if you want, but that means if it's going downwards, then it means that you're decelerating, which doesn't make sense to me. So I always usually put the positive. Okay. So what I usually do here is I collect all the information that I need. So the displacement, we don't know. That's what we're trying to find in part A. The initial velocity is already mentioned as 21 meters per second. Okay. The final velocity, now this one's an interesting one because it doesn't mention about final velocity, but because we're finding the greatest height reached by the ball, that means when the ball stops at the greatest height, the final velocity is 0. The acceleration I consider to be minus 9.8 meters per second because we're going upwards. We're going upwards and the ball is decelerating, okay? And the time we don't have, so we don't know. Okay, let's do this then. So, let's consider the equation v squared plus u squared equals 2as. Because we don't have a time, and time's not considered in this equation. So therefore, we are going to use this. All right, let's switch this a second. There we go. All right, so what's happening here? Let's plug in all the equations. So what we have is 0 squared equals 21 squared plus 2 times minus 9.8 times s. So obviously, you rearrange to sort s out. S is equal to 441 over 19.6. Because, yeah. And that is equal to 22.5 meters. Therefore, the greatest height is equal to 22.5 plus 7. Because don't forget about we started at 7. And it's the greatest height from the ground. So therefore is equal to 29.5 meters above the ground. Excellent. All right, superb. So question B, let's do this. So the time of a flight of the ball. All right. So, the time of flight of the ball. Time of flight, the total time of motion. Right. Let's see. Question B. So, the time of the flight of the ball. Right. What we can do is... So, the time of flight is the total time that the ball is in motion from the time that it's projected to the time that it stops moving. Here the ball will stop when it hits the ground. The point at which it hits the ball is 7. So below the point is minus. Right, okay. S is minus 7 because it's below the point of which the ball hits the ground. U, not U, U is 21 meters per second, minus 7 meters. V, we don't know. So, who knows? The acceleration is minus 9.8 for now. Seconds. Okay? So, and what we're going to do is that we're going to equal time equal t. So what's happening here, when we consider the equation v equals ut plus half at squared, what we get is minus 7 equals 21t plus t equals t, so a half, minus 4.9 t squared. So therefore, we rearrange the equation, we will get 0 equals 4.9 t squared minus 21t minus 7 equals 0. Well, so using quadratic formula, we will get that t is approximated to 4.5965, already did the maths for this, equals minus 0.3108. Okay, so we completely discard the negative time because it's impossible to have negative time. So then we approximate this to usually either 2 or 3 significant figures. So we're just going to say 4.6 seconds, and that's it. Okay? Now, I feel like you're confident enough to tackle some more harder questions. So, tackle more questions. Alright, these are questions 6, 7, 8. Right, so these are questions 6, 7, 8. If you want to pause this video right now, and then you can try these 3 questions if you can. Any problems, just put a comment or whatever. And thank you very much for watching. And the next episode will be on variable acceleration. I hope I explained clearly enough, or at least that you understand some points here and there. Okay, thank you guys for watching, and see you in the next episode. Bye-bye.